Hello friends, the topic for today is fundamental concepts in digital electronics. The term digital is derived from the way operations are performed by counting digits. For many years, applications of digital electronics were confined to computer systems. Today, digital technology is applied in wide range of areas in addition to computers. Such applications as television, communication systems, radar, navigation and guidance systems, military systems, medical instrumentation, industrial process control, and consumer electronics use digital techniques. Today's video introduces you to digital electronics and provides a broad overview of many important concepts in digital electronics. Let us start. Welcome to our channel Engineering and Technology for You. If you are not subscribed to the channel, kindly subscribe and press the bell icon so that you get notifications for future videos on this subject. The topic for today is fundamental concepts in digital electronics. Let us start with the introduction. The term digital is derived from the way operations are performed by counting digits. Now here by digits we mean in decimal it is 0 to 9, but binary digits are 0 to 0 and 1. Now, many years applications of digital electronics were confined to computer systems. Today, digital technology is applied in a wide range of areas in addition to computers. Such applications as television. Now, television, when we talk about television, we have digital channels in television. Then communication systems, we have digital communication systems. Then radar, navigation and guidance systems. Now nowadays everybody is familiar with the Google Maps. So that is the navigation and guidance system, which is also digital. Then military systems, medical instrumentation. We have a lot of instruments which are digital in medicals. Then industrial process control and consumer electronics. So all these consumer electronic includes whatever you are using in day-to-day life. So that use the digital techniques. So over the years, digital technology has progressed from vacuum tube circuits to discrete transistor to complex integrated circuits. So earlier, the vacuum tubes or the valves, triode, pentode, those were the circuits used. And then we came to the discrete transistors, that is the bipolar junction transistor, BJT, FET, MOSFET, and so on. And then we are coming to the integrated circuits, it is the ICs, on which many contains millions of transistors in a single chip, and many of which are programmable. So that is what the digital technology has moved to. So the ICs, they are programmable. You'll see the programming in future videos. Then digital and analog quantities. So electronic circuits can be divided into two broad categories, digital and analog. So digital electronics involves quantities with discrete values. So discrete values means they are not, they are individual values, they are not attached. Whereas analog electronics involves quantities with continuous values. So it will have the continuous values. Whereas this digital electronics will have only the discrete values. Although you will be studying digital fundamentals in this subject, you should also know something about analog because many applications require both, particularly when we are converting from analog to digital and digital to analog, we'll need some knowledge of the analog circuits. So interfacing between analog and digital is also important. Then let us see what is analog quantity. An analog quantity is one having continuous values. Most of the things that can be measured quantitatively occur in nature in analog form. So here most of the things like uh, we have the time, pressure, distance, sound, all these which occur in nature, they are in analog form. So for example, here we have taken the air temperature changes over a continuous range of values during a given day. The temperature does not go from 70 to 71 instantaneously. So it takes all the infinite values in between. So it is a continuous change. So if you are taking a graph of the temperature on typical summer day, so here you'll find a smooth continuous curve. So here we have taken temperature in Fahrenheit, and this is the graph of the temperatures. So starting from say night 12 a.m. and then 1, 2, 3, 4, and this is the afternoon, and then again here these are the hours, peak hours, and then evening we have PM. So this curve is a continuous. That's why the analog quantity is a continuous quantity. So when we are plotting, even it is not taking the values which are shown here. It is taking the values which are in between these two. So these are the say from 75 to 70. There can be number of values. So other examples of analog quantities are time, pressure, distance, and sound. So these are some common examples. Then let us see the val sampled value representation or quantization. So if the graphing the temperature on a continuous basis, we just take the temperature reading every hour, and now you have sampled values representing the temperature at discrete points in time. So that is every hour over a 24-hour period. So now here we are taking the values of temperature at say every hour. So 1, 2, 3 like this. These are the uh, particular. Say this is 12 a.m. This is 1 a.m. So this is the value that is 95 like that. So here the graph now has changed. It is not continuous. It is discrete in nature because every value is represented individually. It is distinct from the other, and there is no continuation between. They are disconnected. There is no continuation here. So if you plot the same graph here, we get the so you are actually converted the analog quantity to form that can now be digitized by representing each sampled value by a digital code that consists of series of ones and zeros. So here if you take any value, for example if you take this value, now here this represent the value 95. So this 95 now it can be this is the sampled value, so we can represent it with a digital code that will have the series of ones and zeros. That is what we mean. So we'll be able to represent this 95 with series of ones and zeros. Then binary digits. Let us see what is binary digit. So each of the two digits in binary system. So when we say binary, it means two. So it has two digits, 1 and 0. So each of the digit is called a bit. So that is nothing but the binary digit. So this bit is a short form of this binary digit. So in digital circuits, two different voltage levels are used to represent the two bits. Generally, one is represented by the higher voltage. Now we represent it as high, and 0 is represented by lower voltage, which we refer to as low. So this is called as the positive level. When we represent high, 1 with high voltage and 0 with low voltage, we call it as the positive logic. Then there is another system which 1 represented by low and 0 is represented by high. So that is called as the negative logic. So it is just opposite to the positive logic. So in negative logic, the high will be 0 and low will be 1. So the group of bits, that is combination of ones and zeros, they are called as codes. So when we combine say 4 zeros, 8 zeros, then there is group of bits that we call it as the code. So codes are generally in the form of group of bits, ones and zeros. So they represent letters, symbols, instructions, and anything else required in a given application. For example, see the numbers, letters, and symbols. So these are all present on the ASCII keyboard. So they are represented with the ASCII code. So ASCII code, it is a 7-bit code with one more bit for the parity. So that will represent, and that will be, for example, a letter A will be represented by 41, like that in ASCII. So that is, we call it as the codes. So generally the numbers, letters, symbols, instructions, all can be represented with these codes. That is group of bits. Then let us come to the logic levels. The voltages used to represent 1 and 0 are called logic levels. So ideally one voltage level represents a high and another voltage level represents a low. So in practical digital circuits, however, high can be any voltage between a specified minimum value and a specified maximum value. It's actually practically, it will not be only single value, it will be any value between a minimum value and a maximum value. And similarly, low can be any voltage between a specified minimum value and specified maximum value. Then there can also be no overlap between the accepted range of the high levels and the accepted range of low level. There should be no overlap. So here this figure illustrates the general range of low and high for a digital circuit. Let us see what is it. So here the variable VH max represents the maximum high voltage value and VH min represents the minimum high voltage value. The maximum low voltage value is represented by VL max and minimum low voltage value is represented by VL min. So the voltage values between VL max and VH min are unacceptable for proper operation. So voltage in the unacceptable range can appear as either high or low to a given circuit. So it is we can't predict what will be the value. So that's why high here you can see this. This is the range for high VH max and this VH min. So that is representing binary 1 or high. Similarly, VL max and VL min, that will represent binary 0 or low. So now this range of VH min and VH max. So the values for VH and VH minimum and VH max will depend on the particular digital family. So for example, the for a CMOS, there is complementary MOS. This is 2 volt to 3.3 volt, and low input values may range from 0 to zero point 0.8 volts. 0 to zero point 0.8 volts. So in this case, the circuit will accept as high or binary 1. If a voltage zero point 0.5 is applied, the circuit will accept it as low and a binary 0. So, and the voltages between zero point 0.8 and 2, they are unacceptable, because that will not uh, say, it will not represent anything. So here we are having VL minimum 0, VL maximum 0 0.8. Then 0 0.8 to 2, they are unacceptable. So VH minimum is 2 and this is 3.3 VH max. So similarly, for other families we have different voltages. Say for TTL, VH max is 5 volts, like that. So then let us go to the digital waveforms. So digital waveforms consist of voltage levels that are changing back and forth between high and low levels or states. So here we have figure 1, which shows the single positive going pulse generated when a voltage or current goes from its normal low level to its high level and then back to its low level. So you can see it's positive going pulse. So this is now normally this is low. Then when it goes from at T0, it will go to high. So and then it will remain high for a certain time. Then at T1 it will go low. So this is positive going pulse because it is going from low to high. Then similarly, if you look at this negative going pulse, so here negative going pulse is generated when the voltage goes from normal high to low. So at T0, from high it goes to low voltage and back to its high value. So it will stay here for low during T2 to T1, and then at T1 it will go high. So this is the negative going pulse. A digital waveform is made up of series of pulses. So positive pulse and negative pulse. So we can have a series of pulses, positive or negative, and that will form the digital waveform. Then let us see now here you can see the rising or leading edge. So when it is going from low to high, we call it as the rising or leading edge. When it is going from high to low, then we call it as the falling or trailing edge. So similarly here, it will have the falling edge this side, and here rising edge this side. So for positive going, the rising edge and will be this leading edge, whereas for this the falling edge will be the leading edge. Then pulses. A pulse has two edges, a leading edge that occurs first at time 0 and a trailing edge that occurs last at time t1. So for positive going, the leading edge is rising edge and the trailing edge is falling edge. Then the pulses in both the figures A and B, they are ideal because the rising and falling edges are assumed to change in zero time, that is instantaneously. You have seen a sharp rise or sharp fall. In practice, this transition never occur instantaneously, although for most of the digital work you can assume ideal pulses. Then the waveform characteristics. Now, most waveform encoded digital systems are composed of series of pulses, sometimes called pulse train, and can be classified as either periodic or non-periodic. A periodic pulse waveform is one that it repeats itself at a fixed interval called a period T. The frequency f is the rate at which it repeats itself and is measured in hertz, that is the unit for frequency. Then a non-periodic waveform does not repeat itself at a fixed interval and may be composed of pulses of randomly differing pulse width and randomly differing time intervals between the pulses. So here, if you look at this figure, now here we have the periodic square wave. So it will repeat itself at a fixed interval. So here you can see this is the positive pulse and this is the negative pulse, and again it is repeated. So this T1 is the total period of the square wave. Then T2 is the second period, T3 is the third period. So it will have the periods T1, T2, T3 and so on. And the frequency of this square wave, it will be given by 1 by T. So this is periodic because it is repeating itself after a fixed interval. Whereas if you look at this waveform, it is a non-periodic. It does not repeat itself at fixed intervals, and it is composed of pulses of randomly differing pulse widths. You can see this is very narrow, whereas this is broad. Again, this the width is more. Again, it has become narrow. Here again, it is in between these two. So this is randomly differing pulse width, and the time interval is also different. So it is a non-periodic wave. Of course, both are digital because it is having only say high and low. That's all. Then waveform characteristic. The frequency f of a pulse, that is digital waveform, is the reciprocal of the period, and the relationship between frequency and period is expressed as follows. So f is equal to 1 by t and t is equal to 1 by f. They are the reciprocal of f is reciprocal of t and t is reciprocal of f. Then another characteristics of periodic waveform is duty cycle, which is the ratio of pulse width, that is tw, to the period t. It can be expressed as percentage. So duty cycle is the pulse width divided by t into 100. So if you are taking square wave, the duty cycle is 50%. So here you can take the tw. Here you can take t high, and you can take here t high plus t low. So that is the total period, whereas the period of high is tw. So that is how the square wave, since it is having the duty cycle is 50%, just because T low and T high both are equal. So if you are going to divide T high divided by T high plus T low, it is going to give you 50%, 1 by 2. So with this, we come to the end of this video. If you have any questions, you can contact me on Facebook, Twitter, Gmail and Instagram. Then if you like the video, press the like button, share with your friends and subscribe to our channel Engineering and Technology for You. And don't forget to press the bell icon if you want to get notifications for future videos. Then thanks for watching. Have a nice day.